Okay, here we'll take a look at another sample problem. So it says the electric potential at P located at the center of square of point charge. The distance D is 1.3 centimeters. So this is a square shape, and we like to consider the electric potential at the center of this square. The distance is D, and the charge is Q1, Q2, Q3, Q4. So this is nothing special. We would just like to calculate this. Is D is D over square root of 2. Yeah, because this is a square and at the center point, so all the way 45 degrees. And in that case, this is D over square root of 2. Okay, so this is easy. So we have R equals D over square root of 2. And V equals summation Vk, K is from 1 to 4. So we have 1 over 4 pi epsilon naught times Q1 over R plus Q2 over R plus Q3 over R plus Q4 over R. Okay. So so this is nothing but we can all the way factor out the 1 over R. So we have 1 over 4 pi epsilon naught, and then times 1 over R. R is D over square root of 2. So we have a Q1 plus Q2 plus Q3 plus Q4. So this is 8.99 times 10 to the 9th power times 1 over E is 1.3 meter. So 1.3 over square root of 2 times Q1 is 12 plus negative 24 plus 31 plus 17 times 10 to the minus 9. Don't forget the nano is 10 to the minus 9. So this number is 330 volt. Okay. Yeah. But actually, it just tells you that the equal potential surface will be something like this, this shape. Yeah, maybe you probably need to calculate it by a computer software. You just try to calculate the point one by one, and then you can just connect them together. Yeah, probably need a computer software to calculate, but actually not so difficult because you only need to write some for loop, and then you calculate the distance between different points to the 4 charges, and then you just add this term together. Actually, these are the same. What we only need to calculate is the R1, Q1 over R1, Q2 over R2 for different point over the space. Then you may be able to find the equal potential difference like this. And not necessarily this shape, I think, but maybe this is the correct way. But yeah, at least you know that is this is a positive charge, positive charge, positive charge, negative charge. So at least what we know is that the equal potential surface should be somehow separating the positive charge and the negative charge, somehow like that. Yeah, but why the shape should be like that is difficult. It's difficult. You must refer to a computer software to do this. Okay, so the next sample problem. So we have 12 electrons are equally spaced and fixed around circle of a radius r relative to V equals 0 at infinity. What are the electric potential and electric field at the center C of the circle due to those electrons? Okay, so for this case, so we have V equals 1 over 4 pi epsilon naught times negative 12e, negative 12e. Actually, everyone is negative e, negative e, negative e, all over capital R. So when you just add them together, it is nothing but negative 12e over R. So it is straightforward. Straightforward. And if you really like to calculate the electric field, yeah, it also asks you not only the electric potential, but also the electric field at center. So actually, in this case, you can see they are all the way electron, which means that for this one, it generates the E field pointing this way. For this one, it generates the E field pointing this way. So it will cancel. So actually, E will be 0 at the center point. Okay, so the question B is if the electrons are moved along the circle until they are non-uniformly spaced over 120 arc, what are then the potential at C? How does the electric field at C if at O? If at O. Okay, so in this case, suppose there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are still totally 12, and the distance doesn't change. So the V doesn't change at all. It is still this way. As much as we consider this point and the distance from all the charges to this point doesn't change, then the potential difference won't change because we only calculate the algebraic sum, not the vector sum. But for E, it doesn't equal to 0. It doesn't equal to 0 because they cannot cancel at this point. They cannot cancel. Maybe for cancel partially cancel, but generally will point to somewhere this way or maybe lower. But yeah, it's hard to tell. But the only thing we can confirm is that E is not 0 for part B. So this is the case that V will be the same and E are different. Similar to this case, V will be the same, E are different at a point only. Okay, so next we will we come up with this potential due to the electric dipole. So actually we have tried to calculate the electric field due to electric dipole. So if you still remember, an electric dipole is like there are a pair of charges with the same magnitude but opposite sign, keeping in a small distance d. So yeah, at that time we only calculate the E field on this z-axis, But now for the net potential, now we can calculate something different. We can actually calculate something in the space, not only on the z-axis. So now we consider V equals V plus V minus because there are only two charges. We just calculate both of them and then add them together. So for V plus, it is nothing but 1 over 4 pi epsilon naught times Q over R plus. R plus is this one. R is from the center point of the dipole to the point P we concern. And then R plus is from the positive charge to P. And then R minus is from the negative charge to P. So here we have 1 over 4 pi epsilon naught Q over R plus negative Q. So this is negative Q over R minus, like this. Okay, so we just add them together. We find the common denominator, and then we just add them together. So it becomes, we just factor out Q. So we have Q here over 4 pi epsilon naught in front. And then we have R minus multiplied to here, R plus multiplied to here. So we have R minus R plus, R minus R minus R plus. and then the common denominator is R plus times R minus. Okay, so we look like this, and then let's see how we can simplify it a bit. So we can approximate the two lines to P as being parallel and their length difference as being the leg of a right angle with hypotenuse D,斜边. Okay, so we just assume that the point P is far away. Still, we have the far field assumption, which means that this point is far away. If it is far away enough, we can assume that this line and this line are parallel, and so as this line. This is something strange if P is very close, but if P is sufficiently far away, then we can assume that R plus is parallel to R minus. R plus is parallel to R minus, and R is lie between, although we don't really need that here. So we still have D, the distance between the two charged particles, and we assume the angle here is theta. The angle here is theta. Oh, actually, we still need that one. We assume theta. Theta is the angle between the z-axis and OP. And OP, this is theta. So if we assume R plus R and R minus, these three lines are all parallel, then this theta is this theta will be the same. Okay. So the next is that we will try to find the approximate value of R minus minus R plus. So we will assume that our point P is here, point P is here, point P is here. If we assume that P is infinite far away, then R plus minus R minus will be this segment. Will be this segment. R minus R plus. So R minus R plus, using the trigonometry you learned in high school, this is D, this is theta. So this is R minus R plus. So R minus R plus is divided by D will be cosine of theta. So R minus R plus is D cosine theta, like this one. Of course, with it is only approximately equal, and R plus times R minus, we can directly assume it to be like R squared, because this is like if this is R, the middle one is R. This is something like R plus this one. This is somehow like half of R minus R plus. This one, maybe we can call it delta R. So it is somehow like equal to approximately equal to R minus delta R plus delta R. So it becomes R square minus delta R square. And suppose R is quite far away from this one, then this is approximately R square. So we have this one. So we just plug in this one and this one to here. So we have a Q over 4 pi epsilon naught D cosine theta over R square. And if you still remember, for the electric dipole moment, we have a P equals QD. So QD can be written as P. So we have P cosine of theta times 1 over 4 pi epsilon naught over R squared is the potential generated by the dipole. So next, we try to consider something more difficult, which is like a potential due to continuous charge distribution. So similar as before, if we have a discrete charge, we can just calculate one by one, and then we just add them together. But with continuous charge distribution, even for electric field, then we need to find, cut it into many small charge packet or charge, small charge, DQ, something like that. And then for this small charge, you can consider the charge is uniform, and also the distance can be a single distance. So in that case, here, for the case here, we also consider this way. If we have the continuous charge distribution, we try to separate the charge into many small segments, divide the distribution into charge element dq that can be treated as particle. Then we just add them together using the integration. So it is something like, V is integration of dv. Just add all the small dv together. Okay, so so dv. So dv here is nothing but 1/4 pi epsilon naught times dq over r. Because we have if we have a discrete charge, we will write it as v equals 1/4 pi epsilon naught times q over r. So we write it like this. For small charge, and then it generates a small potential, and then we just add them together. So we just plug this one into here, and then 1/4 pi epsilon naught is a constant, so it simply look like this. Okay, so next we will try to consider the potential generated by line of charge. So this dq equals lambda dx. Just as what we worked before, which is like dq is the line charge density multiplied by the length. So this is nothing special. And this is what we write in the previous page. And here we will try to calculate the electric potential generated at point P due to this rod. We have a charge rod. Here, length L, with some charges, and then it will of course generate some E field and also electric potential in the space. What we only want to find is the potential at this point. So we try to separate this whole rod into many small segments. Everyone is dx on it. There are dq charge on it. So for every small charge packet, it will generate potential at this point, and we just add them together using the integral. Okay, so the distance from point P to here is d. And actually, for every small packet, we will consider the x-axis here. Maybe from this is 0 to L. So probably we will integrating dx from 0 to L. And actually, the distance from this packet to this point P will be r. And according to the Pythagorean theorem, r will be square root of d squared plus x squared. So dv is this one. So we have r equals to square root of d squared plus x squared. So we substitute it here. And of course, dq equals to lambda dx. So we have lambda dx here. So it is dv pretty much like this one. So we can try to find the v by integrating dv. And so we substitute dv by this whole term. And of course, lambda over 4 pi epsilon naught is a constant. So we just factor it out. And then we have a dx over square root of x squared plus d squared. So if you just use the appendix e, we have some form of integration. It is just like this integration is lateral log of this term. So actually, if you like to derive this integration, it is just like, so you probably need to define x to be d tangent theta, and of course, if you draw a right angle triangle, you will have something like, let's say this is d, this is this is d, this is x, this is theta. Yeah, so this is L, this is let's see. Sorry, it should be L D, and then this is L square over L square plus D square. This is theta L, yeah, something like that. And then this, so we have a theta L equals or I mean tangent of theta L equals L over D, because we need to substitute this variable. Okay, so in this case, we have a dx equals d secant square of theta d theta, and then x square plus d square equals d square 1 plus tangent square of theta, which is d square secant square theta. Okay. Yeah, it's like that. So here we have 0 to L, 1 over square root of x squared plus d squared dx. So we have dx to be d secant square of theta d theta all over square root of this one, which is d secant theta. And then substituting x to be 0, it will be x to be 0, then theta will be 0. And then substituting x to be L here, then it is actually theta L. Okay, so yeah. Okay, so now we can do some cancellation. D and D can be cancelled. Secant square and secant can be cancelled. So the remaining part is integrating secant of theta d theta from 0 to theta L. So the trick here is that we can just multiply and divide this by secant theta plus tangent theta. And then, yeah, we also have secant theta plus tangent theta d theta. Okay, so now we can just let let's say y equals secant theta plus tangent theta. So we have dy equals secant theta tangent theta plus secant square theta d theta. Okay, and then if you look at this one, this is secant square and then secant tangent, which is actually this one and this one. This should actually this one and this one. So this one is synced to something like dy over y, something like that, and it turns out to be natural log of y, and y is actually this one. So we have a 0 to theta l, and then natural log. Sorry, it should be theta equals 0. Theta equals 0 to theta equals theta L, something like that. Okay, so we have a lateral log of secant theta plus tangent theta, evaluate from 0 to theta L. Okay, so when you look at secant theta here is like secant theta is like square root of L square plus D square over D, and then tangent theta L is like L over D. So we have natural log of square root of L square plus D square plus L all over D, like this. If we just plug in theta equals 0, we have secant 0 is 1 because it is 1 over cosine 0, which is 1 over 1. And then tangent 0 is 0. So this one is 0. So it turns out to be lateral log of square root of L square plus D square plus L all over D. So we pretty much derived this quantity or this equality. Okay, so next we will consider the potential. The potential due to the continuous charge disk. Okay, so here in figure we consider a differential element consists of a flat wing of radius r and radial width dr prime. Its charge has magnitude dq, like that. So we will try to calculate the electric potential generated by this disk. And similarly, we just separate into many rings with different radius from 0 to capital R, and we try to find the electric potential over the z-axis. Okay, so let's see this orange ring. So we have sigma to be the surface charge density, multiplied by the area of this ring. You can also try to cut it and then try to expand it. It will become a rectangle if the this ring is very thin, and the height of this ring will be dr prime. So this is r prime axis, and then the length will be the circumference of a circle. So this length will be 2 pi r prime. So the total area for this ring, the area will be 2 pi r prime dr prime, like this. So this is nothing but the dA. So this is dA. which is the surface charge density multiplied by the area will be the total charge at this on this ring. Okay, so next we have this expression, which is just the definition, or just we derive it just now, or yeah. So we can just plug in this one into here. So we have sigma 2 pi r prime times d r prime. And then similarly, we consider the ring with radius capital R, and then we consider the point, which is Z from the plate. So actually the for the ring, for every small segment on this ring, the distance from this ring to here will be nothing but a small r. And using the Pythagorean theorem, which is nothing but r prime square plus z square, and then take the square root, which means r equals square root of capital R prime square plus z square. So we can just put it here. So here we have a dq like this, and then this is R. Okay, so next we can do some simplification. So we have 2 pi here. This is 4 pi, so we have 2 here. So we have 2 epsilon naught here. Sigma is also a constant to R prime, so we have sigma over 2 epsilon naught. And then we actually need to integrate it from 0 to this one should be R. Yeah. So so the remaining term will be R prime dr prime here, and then square root of this term. So this integration is a bit easier. It's quite easy. We don't need the trigonometry, because for this one we can simply use the chain rule, something like the chain rule. dr prime square will be nothing but this one, and we actually can also add a constant to it, because z is a constant to r prime. So we add a constant here. We just take the derivative of constant, will be 0. So it doesn't really matter. So as much as we have this term, we also have this term here. So we can just regard this thing is something like y. This is a square root of y, and then it is something like integrating y to the negative 1/2 power dy. So this one will be nothing but y to the negative 1/2 power plus 1 over negative 1/2 power plus 1. So this is y, square root of y over 1/2, which is 2. Yeah. Oh, sorry. This here it also should have a 1/2 factor here. Because if we have a dr prime square should be 2r prime dr prime, something like that. So here we only have r prime dr prime, so we have a 1/2 factor here, and then these 2 and these 2, this 1/2 will cancel each other. So finally we only have square root of y, and this y is actually c squared plus r squared. So it is like sigma over 2 epsilon naught z squared plus square root of c squared plus r squared, and then we evaluate from r R prime. This is R prime. R prime from 0 to capital R. So we just plug in R prime equals to R. We have square root of C squared plus R squared, which is this term. And then we also substitute R prime equals to 0. So it becomes square root of C squared, which is Z. So we have this expression. Okay, so note that the variable in the second integral is R prime and not Z, not Z. So this is the expression of the electric potential generated by a charge disk with a uniform charge distribution. Okay, so next part is just now we consider the work done. The work done is like a integration. We have a F dot ds equals this expression. If we try to find the overall work done, we need to integrating over a path. Now we don't necessarily integrate it out. We just take a small segment here. So now let's see. So the first expression is fine because we just have F equals Q0 times E, Q0 times E. And then F dot ds is the work done. So this is the work done. And then next, we consider this one to be Q0 dV. Q0 dV is like, this is the potential energy because this is the work. This is the work dW. And this is Q0 dV is will be negative du, the negative potential difference. So we have negative Q0 dV, negative Q0 dV. So we just change the work done by the negative of the potential, which is like this. And here we try to evaluate this inner product between these two vectors. So it is like the magnitude Q0e times ds, and then times the angle, cosine of the angle between them, which is theta. So now we can just cancel Q0 and Q0. And then we have dV ds. So we just divide ds on both sides. So ds and ds cancel. Finally, we have negative dV ds here. And then we also have E cosine theta on the left-hand side. Just swap the left and right. Okay, so we have E cosine theta equals minus dV ds, which means that E cosine theta is the E component over the s-axis. So this is, if we just project this E vector on the s-axis, this is E, this is called ES. If we have a s-axis, if we have x-axis, y-axis, z-axis, you can write it as a EX, EY, EZ, and so on. So in that case, we just write ES is the s-axis component of E. S-axis component of E. So ES is nothing but negative dV ds. So why is it useful? Is that before we actually need to calculate the line integral, but now it's somehow like we can actually find the electric potential over the space or over an axis, and then we just need to take the derivative, and then we can find the electric field component over that axis. So this is great because as you have learned the calculus, you know working on derivative will be usually much more easy, much easier than working on an integral. For integral, you need quite a lot of techniques, just like trigonometry or something. But taking derivative will be much easier. And even for computer, taking derivative can use some numerical method to do that with a simple way. So this is great. This is great. And more generally, we can write it as the x-axis component will be the negative dv dx. Take the derivative of the voltage with respect to the x, and then with a negative sign, all the way like that. And generally, we can write it as this form. This form, it looks horrible, but actually, this upside down triangle is called a gradient. It's called a gradient. So this is called a gradient. Gradient. Okay, so it is just like taking the derivative in different direction. In Cartesian coordinate, the gradient is simply like partial derivative of x I hat plus partial derivative of y j hat plus partial derivative of c k hat, something like that. So gradient is what we call an operator. It can operate to a scalar field to convert it to a vector field. So the idea here is that calculating the E field over the whole space might be difficult because if it is a continuous charge distribution, you need to calculate the vector for every small package, and then you need to add them using the vector sum. It will be more difficult. So now we try to find the scalar field, which will be much easier to find because we don't need to calculate, we don't need to consider the direction, we don't need to decompose the vector in different axes, and then we sum in different direction, and then we combine them back again. Here, we find the potential in the whole space, and then we take the derivative in different direction. Taking derivative will be much easier than taking integration in different direction. So in this case, we try to find the electric potential first, and then take the gradient. Then we can find the E field in the whole space. So for some specific way, we can directly find the E field, directly for some easy case. Maybe, yeah, for some case in chapter 22, 23, you can using integration to find the E field, or by integration. And for some specific structure, you can use Gauss law to do that. But for some more difficult cases, you can find the voltage or the electric potential first. So maybe for some more complicated situation, you find the voltage first and then take the gradient. Or sometimes you just need to take the derivative. If you just only need to find it in one direction, then taking the calculating the electric potential first, and then take the gradient of the derivative, and then find the electric field. So the final goal is still calculating the electric field, at least in a physics class or electromagnetism class. Yeah, so there are three approach that is introduced to you, so you can use either of them to some problem. You can feel free to use different approach. For some problem, you definitely, oh, this one is easy enough. Finding this like this is good enough. And for some cases, oh, going this way is not good. Going this way is not good either. Maybe you need to try to find the electric potential first, and then take the derivative or take the gradient. So just now we mentioned that v is negative, the line integral of the E field, and actually you have the integration of E to be v, and now you can also take the derivative of v, take the derivative in 3 dimensions, which is a gradient. It becomes an E. So it is a general case of the fundamental theorem of calculus. If you feel interest, you can check it on the Wikipedia. There are plenty of information about that. So in calculus class, you probably know that the fundamental of calculus is like if we have f prime of x to be f of x, small f of x, then if you would like to calculate the f of x ex from a to b, it is nothing but f of b minus capital F of b minus capital F of a. Yeah, something like that. So this is the fundamental calculus in 1 dimension. Because when we come up with the definition of the integral, the definition of this one is from the Riemann sum. Riemann sum. And this is a derivative. Derivative is like we take the limit of delta x tends to 0, and then we have a f of x plus delta x minus f of x over delta x. So this is the derivative. So it's like this one and this one are 2 independent definition. But the fundamental theorem of calculus tells you that actually, if you like to calculate the definite integral, you can just find the antiderivative, and then you will plug in the value, and this is done. And this is the fundamental theorem of calculus for line integral. Okay. So let us stop here today. I'm a bit over time.